Okay, in this particular problem, we're going to drag this box along the floor, pulling on with a rope that's at a certain angle. So we can put in some angle here. I'm not going to use any numbers because that's kind of the point of this problem. High school students really want to use numbers, and sometimes you don't have numbers, so you just go with things that we call symbols or variables, and you just put in what you know, and you don't worry about it because you know it's all going to work out good in the end, so you're pretty excited to find out how it's going to work out. So in this case, I'm pulling along at an angle with the red arrow, at a certain angle, and I'm doing it at a constant velocity. Now, constant velocity, by now, I hope you know what that means. That means that there is no acceleration, and no acceleration means there's no net force. So that means there's no forces left over. I don't want to say there's no forces, because there are clearly forces on here, but the forces going forward and going backwards would balance out, and which means we need another force on here that would be going back this way. That, of course, is friction. Friction always goes the opposite way of the force that we are going with forward. So I'm going to put F on here. And F is what we're actually trying to figure out. We're trying to figure out what F is. Now, we clearly have another force on here. We have weight, which would go down, which would be M times G. Sometimes in the problems, they give you a weight in newtons, so therefore you don't have to multiply anything together. Sometimes they give you a mass of the box in kilograms, and then you have to multiply it by 9.81 to get the weight. So depending on what they did in this problem, they might have given you a weight or they might have given you a mass. So I'm just going to put mg there just in case. Okay, so this red force here can be resolved into a force over and a force up. And what we know, we're always trying, all these problems, we're trying to start with a common sense kind of beginning equation so that we can derive for what we want. And what we know in this particular case is constant velocity means any force going forward, which would be this one, has to equal any force going backwards, which of course would be this one. Now, this is why everybody's having a problem with this particular problem, is because you're thinking, how can I find these two green forces over here if I don't know the red force? I need to find the green forces so that I can find the red force, but I don't. So it's like a vicious circle. Well, we do know what these green forces are. They are, this one is F sine of theta. See, we don't worry about numbers right now. We know that this is F sine of theta. It's the opposite one, and this one here is the F cosine of theta. So we know what those are. And so our starting problem here that we want to use is, and we know that this force going forward, or the F cosine of theta, has to equal the force going backwards, which was friction. So we just start subbing things in here to figure out what we know. So we're going to have F cosine of theta should equal friction, and friction, if you remember the equation for friction is the product of two things, mu and normal force. Now this normal force here has been tricky for a lot of you. It's not net force. Net force is a force that we never draw on here. Normal force is all perpendicular forces, all of them. It's not just normal, not just the weight. Sometimes it is just the weight, but it's not always just the weight. In fact, in this case, we actually have two vertical or perpendicular normal forces. We have a mg going down, a weight, and we also have the green force going up. So when I put this friction in here, I'm going to put mu times normal force, which would be this force right here, mg, minus this force right here, F sine of theta. I'm going to have to rewrite that so it looks a little bit better. So now what I have is I have F cosine of theta equals mu. I'll go ahead and multiply the mu through. Mu mg minus mu f sine of theta. Okay, and so you'll notice here that we can combine our f terms. We're trying to solve for this. This is the whole point, to try to solve for this. So I can get my f's on both sides, and I could do f cosine of theta plus mu f sine of theta would equal mu mg. Okay, and so then I could factor out an f, and I would factor out an f, and I would get cosine of theta plus mu sine of theta should equal mu mg. And then we can get one equation. If I put it up here, I'm running out of room here. We'll do f equals mu mg all over cosine of theta plus mu sine of theta. And if you look at the problem, I think there's a couple problems on there like this, and there will be one on the test and the final and everything else. You have mu. Mu is given the problem. You have either the weight or you have the mass, which means you can figure out what mg is. If you have the weight, then you'll just put the weight instead of mg. And you have the angle that we're pulling it along, and again you have mu. So you have everything you need to fill in to figure out what this the force in the rope is. And so what we can do from now on is, and this is what we try to do in physics, is I mean, this is an equation. I mean, you call this, Herman's equation. You call it whatever. It's not an equation you find in a book. It's just if you ever have the situation where you're pulling a box at an angle with a rope at a constant velocity, and you want to figure out what the force is in the rope, we now have an equation that we can use for that forever. So you don't have to derive this out every single time. I mean, it might be a good exercise to derive it out, but now in the future, when we get this exact same kind of a problem, okay, now keep in mind, it can't be accelerating or anything like that. It has to be pulling along the ground at an angle at a constant velocity. Then we have an equation here that we can use from now on. We can plug those in. So we don't really have any equations in any of these problems. We just have, it is what it is there with forces, and we need to figure out what needs to equal what, or constant velocities or accelerations. That's the first thing we're looking at. And then we can derive for what we're trying to solve for there, and everything else is going to cancel out, and we're going to be able to plug in what we need in the problem. Hope that helps with that. So we'll QED that and call it good.